Okay, so in part 4, I want to go through different forms of simulation that are part of the Virtuoso environment. And the first one's going to be pretty basic. We're just going to do a schematic simulation. And so to do that, I'm going to use our NAND 2 part that we've used before. But in this case, what I want to be able to do is to create a schematic that holds that NAND 2 part. So pick a new cell view, window popped up behind. So I'm going to call this one NAND 2 test, and it's just going to be a regular schematic, and I'll hit OK. And I'm going to go ahead and place an instance of our NAND 2 part. And so I can come down either to this window down here and grab a NAND 2 and put them into the design. The next thing I want to be able to do is to place the stimulus for this, and so this is just like it would be in any other PSpice simulation. We're going to be able to go to place an instance, and I'm going to change my library to the NCSU analog parts, and I can browse through here and find, for example, voltage sources. And in voltage sources I can find my V pulse, and so I'll need two of those, one for the A and one for the B input. And then I'll also want to just have a regular voltage source that's a VDD, and that would be under supply nets. And we'll put a VDD, and I'll also put a ground. So also I'll need to put a voltage supply itself, so I'll need a VDC. So the only thing that's left to do in this layout is to assign properties to these two pulsars. And what I want to be able to do here is to set the voltage for the pulse to be 2. The delay for this first one will be 0. The rise time will be 1 nanosecond. The fall time will also be 1 nanosecond. The pulse width will be 10 nanoseconds. The period will be 10 nanoseconds. And there's no DC bias or anything else. And that will give me a nice little square wave. We'll do the same thing here, only our delay time is going to be offset by 1/2 period. Oops. I always want to put that extra n there. 1 nanosecond up, 1 nanosecond down, and our pulse width will be 10 nanoseconds, and the period will be 20 nanoseconds. Alright, so we at this point have a working schematic. I'll do my check and save and see that everything is acceptable. So the next thing we're going to do is we're going to generate the actual simulation using the analog design environment. And I'll use the schematic editor here and launch ADEL. And I've got to do a bunch of setup things here. So I have to make sure that we're on the right design. NAND 2 test, that's correct. I need to choose the right simulator because by default it's HSpice, as it was before when we did a digital simulation. I want to choose Spectre for this one. I want to choose the model libraries, and since we're simulating using the U of U tools, I'm going to have to navigate to the U of U directory and look for the ELC files and grab the AMI06.scs file. The everything else in here is doesn't need to be touched. Under analyses, I want to choose a transient simulation, and I want it to run for some length of time. We'll do 300N. And the next thing I want to do is choose what gets plotted. And so to do this, I'm going to do a select on design. If you click on a node, it'll give you the current. If you click on a wire, it'll give you the voltage. And so I want the voltages for those three signals. And at this point now, I am ready to do a simulation netlist and run. And what we see here is kind of hard to see on the screen just because the colors aren't really great choices. And we've lost the names of some of these nets. So I think that was our output. If I go back and look at the design here, sorry, net 1, net 2, and net 3. Looks like net 2 is 0 the whole time. Oh, okay, so it didn't actually change my parameters when I set them. So what I need to do now, okay, pressing enter on that screen actually seems to be the trick. So we can run this again. Okay, now we actually have some results, and it's kind of interesting. We see that the voltage kind of descends into a steady state, but there is an interesting little charge up of that capacitor. Sometimes it's a little bit easier to see these things broken out, and so for instance what we can do is right click on one of these guys and do a measurement and move it to a new strip. And what this will allow me to do is to see each one kind of isolated from each other. We can also go in and change properties. Like this guy's a little hard to read, I think, and so we can come in and change the color, maybe make him a little bit brighter. We could even change the width, so now it's a little bit easier to see on a screen. And the nice thing now is I can go back to the original design, for example, and let's say we simulate this capacitor at Q, and instead of it being 1 puff, what if it's 1 nanofarad? I'll do my check and save, and I'll do a run. Of course, it loses the the strips, but we can see here that, with that nanofarad load, we effectively are fully charged. I'd have to zoom in way in here to see there's like small little changes, but the capacitor has essentially tamped out all of the load. In the previous segment, we used a schematic to perform a simulation. In this segment, we will simulate a CMOS layout view and then compare the results to the same schematic. To do this, we have to first start off with an analog extracted view, and to do that we have to go to the layout. So I have here a NAND 2 circuit and I have a layout view of it, and what I'm going to do is use the verify tool, and I'm going to extract the topology. I want to make sure that I have the parasitic caps set so that when it generates, they'll be present in the extracted model. So that just takes a few seconds to run. And then the next thing we're going to do is we're going to do the LVS, the logical versus schematic simulation. And in this view, what we're going to do is compare the schematic to this extracted view. And first of all, we'll run and make sure that we have no errors. So it says netlists match, so that's what we're looking for. And then the next step, this last step, is we're going to do the build analog. And I'm going to choose the extracted parasitics to include all of them. And at this point now, I have an extracted model over here that I can click on. And so this complicated stick figure version is the laid out NAND 2 gate with all of the parasitics computed into it. In order to do a simulation from here, I need to go back to my test module, and I'm going to make a new cell view. So I'm going to do File, New, Cell View, And in this place, what I want to do is choose a config type. So with this, I'm not sure 100% what config means, but that's the type that we're going to have to use. And what comes up is a new configuration. And I'm going to choose a Spectre simulation template. And in here where it says view, I'm going to change this to the schematic view. And in the library list, I want to make sure I choose my video or whatever library you're working in. And the important thing is this view list and this stop list need to be correct. So that's really what this load template did for us. So I hit OK, and it takes me into this screen, and this allows me to see the top cell that I'm going to be building this from, the bindings that we just saw there, and the different parts that it's found. And if I look carefully here at my NAND2, the view is still set for schematic. If I right click on it and do set cell view, I can now change this to be analog extracted. And I'll know that this has worked properly if I go to the tree view and I look at the view here for my transistor, and I see all of the different parasitic parts that were generated from my model. So everything is good. I'll hit save and I can close this now. Okay, so the next step is I want to open up that config view and say yes, open up the both here, and now I can come back to this view and just click on the ADE-L button, and that's going to be our normal simulation. And this is going to be the kind of the way we've been setting things up. So we're going to do make sure that we have the design and its config, and everything else is the same. So I'll buzz through here pretty quick. Okay, so it's now done the simulation. In this case, it is used the layout instead of the normal schematic view. And if we're not 100% sure that that's what's happened, if I scroll up a little bit here, it'll actually show us the component count, and we certainly didn't have 9 capacitors in our original model. The other thing I can do is I can look at these two graphs side by side. So this was the graph of the same simulation that we did before based on the schematic view. And if you notice now, this is a much cleaner, more accurate graph. Some of the weird artifacts that we saw before are gone. Okay, this next part of the simulation is using the analog mixed mode simulation. And what I want to be able to do is to just simulate a system using both analog and Verilog components. And what I have here is a very basic simulation. It has one of the inverters that we built before, a power source, a VDC, and a resistor. So what I want to do to get this started is I'm going to have to make what's called a config view. I've got to configure what elements do I want to simulate, because things like this inverter have a number of different views, cell views. So I'm going to make a new config. So I'm going to change this over here to config, and we'll create this here, a cell called basic, into this project. And the first thing I want to do is click on the use template button to bring up the AMS template, and it fills it in with my view, but we're going to go ahead and change that view name to be a schematic. And that's the schematic that we created over here. We can see here the different libraries, that the different parts that it found in my top cell. So for instance, the resistor came from the HDL lib, the VDC came from the analog lib, the inverter from tutorial, basic from the video, and in particular what view it's going to use. So for instance, we see here the inverter is using the behavioral, which is the Verilog. whereas the resistor is Verilog A, and the voltage source VDC is using Spectre. So all of that is kind of as expected. So what I want to do here is click on ADA Explore. Gotta save this first, and once you save it, you have to close it and come back into it. That's been documented somewhere, and basically it'll pop open a window, the config window back, and it'll pop open the schematic. But now what I want to do is click on the ADE Explorer. This is the new tool, and we're going to create a new Maestro view. So it looks like it's already filled in here. Cell name is basic. The view is going to be Maestro. We'll see it show up over here as Maestro. And this looks a lot like the old ADE, only it has a few additional bells and whistles, especially you can see them over here. So the first thing I want to do is go through here, the simulator. We've got all kinds of different things turned on, so we're going to want that. We could choose different simulation options here. We don't need any model libraries this time. And this is one of the most important ones. This is essentially defining the voltage standard that we expect to be able to use and simulate. And so right now I set up, even though it says 18 volts, it's really 1.8 volts. And it's probably all we really need in this window. In our analysis window, I really want to have that transient voltage like I did before. We'll let it run for 300 microseconds like we did before. In our outputs, I want to do the to be plotted and select on design. And this time, if you notice, it actually opens another copy of the schematic window inside the new ADE window. So I want to be able to plot the output and the input. Of course, they're going to be fairly boring, but it is what it is. And so those are the outputs, and we'll roll here through the simulator. We want to make sure that Spectre is chosen there under Netlist and Run. So for some reason, with my installation, I am having total failure using this first one. And so I have to use the cell view based Netlister, and that seems to work a little bit better. I should also add that when I was running XRun before, if it hit a Verilog's AMS source, it would just core dump. And I've kind of fixed that, but not real well, so that might all be still part of that. So for now, we're just going to click it on cell view based Netlister, and we'll hit apply. And simulation, we can now do Netlist and Run, and hopefully this will work. It throws a bunch of warnings, and well, this time it worked out pretty well. And I know this is like not the most useful graph, but up here is our 5 volt, and down here is our 0 volt for the 2 nets that we're sampling. So very briefly, I've gone to the source code for the inverter, and I've made it no longer an inverter. So I've added a digital clock, and I've added some terrible logic here. So whatever the in is, if in is high, then it's going to be ended with the clock. It is what it is. I don't know, not the best. But we'll save that, make sure there's no errors, and so it's been saved. And what I really want to do is just go back down to the simulation here. So I'm going to open up that. In this case, I can skip the well, I better go into the config view just to make sure that it opens okay. And sure enough, everything's good there, and we'll open up that Maestro view, and we'll hit run. And this should be a little bit more interesting, or it's going to be a total failure. Okay, so at this point, the simulation finished. We can take a look at our waveform window, and if I were to zoom in, there we go. So here we actually can see the square wave that's being generated by our clock inside. And what's really interesting here is, even though it's a square wave coming out of the Verilog, because Verilog would be a straight digital system, That resistor is actually being modeled as a proper resistor, and it has just a tiny bit of capacitance, and we can see that in the rise time and the fall time here that are kind of determined by the system. So this is actually a really accurate analog simulation of a Verilog system, which is really cool.